The story of our nation's air defense has of necessity been a story of rapid changes. Changes in concepts, strategies, and weapon systems brought about by the ever-increasing demands of the time. And though the skies of the future may belong to the age of rockets and missiles, the silhouette of the long-range missile bomber still dominates. The following is a profile of the B-52 and an account of the events of the past year which developed the most powerful bomber ever to patrol the air, the B-52H. Four events of 1960 best illustrate the stages of development and progress of the latest version of the missile bomber. During the latter part of March, the first developmental engineering inspection was held at Boeing's Wichita division to evaluate the innovations to the B-52 which brought about a model change. The new turbofan engines were such a significant change that the engine pod was the subject of a separate DEI a few months earlier. Major interest centered around the airplane mock-up, which displayed such items as the ASG-21 fire control system, the new ECM systems, including a modified shaft dispenser, the numerous changes associated with improved low-level capability, such as the single-motion seat ejection and the bomb navigation system, which incorporates terrain avoidance radar. Air Force acceptance of the planned configuration for the H model during the DEI paved the way for its continued development without delay. The second major phase of development occurred with the delivery of the first 47 body section in August. The H began to take form. With experience accumulated over years of building stratofortresses, the complexity of this airplane presented few problems. Joining of the wings and major sections was accomplished on schedule. The last assembly stage before moving to the camouflage hangar was the change installation where all current ECPs were installed. The rollout of the first H marked the completion of the assembly stage as it was readied for a key pre-delivery inspection. The fourth and last developmental phase was represented by two significant inspections. The contractor's demonstration inspection, held the latter part of November, followed by the contractor's technical compliance inspection. The ground support equipment required for maintenance and overhauling the new systems was demonstrated at the CDI. The majority of the items displayed and demonstrated were applicable to the new model, but some of the items procured for support of earlier models were also included. Immediately following the CDI was the CTCI, which brought more than 170 Air Force personnel to the Wichita Division for a key pre-delivery inspection of the first H model. This was the first opportunity for the Air Force to conduct a thorough scrutiny of all changes included in the first B-52H airplane. Because of the thoroughness of previous DEIs and close coordination during the design of the changes, no major changes were requested. In addition, only a small number of minor changes were necessary to meet Air Force requirements. Behind the relatively short span of a few days of thorough inspection lay many months of experimentation, exploration, and research. The major components which provided a significantly improved airplane over all previous models of the B-52 represent the latest advancement that technology has developed. A major contribution to the superior performance of the new model is the Pratt & Whitney turbofan engines that enable the missile bomber to fly farther than ever before without refueling because of lower specific fuel consumption. The added thrust of the turbofan engine allows system simplification by elimination of the water injection system. Valuable information concerning performance and all pertinent data on the operation of the engine system was collected on a ground test stand and evaluated before the prototype airplane was flown. The G-test bed airplane with the turbofan engines has flown over 100 hours during 1960, with tests being conducted at altitudes up to 60,000 feet. The flight testing explored critical flight conditions, obtained extensive performance data, checked out engine systems, and provided confidence in the B-52H production design. Performance runs with the turbofan engines have shown average specific range improvements over the B-52G of 19.2% for high-altitude cruise conditions. As a missile platform bomber, the latest model of the B-52 has the capabilities of launching 3 different types of missiles, each designed for a separate purpose. All B-52H airplanes are scheduled to be delivered with complete provisions for carrying and launching 4 GAM-72A Quail decoy missiles. The range of the missile is 340 nautical miles at high altitude. Its mission to confuse, dilute, saturate, or otherwise degrade the enemy's radar and IR-controlled air defense systems. This both improves the destructive potential and reduces the cost of strategic bombing missions. Minor modifications to all B-52s previous to the H model were necessary for carrying the Quail. The internal changes were easily made without cost to the plane's performance or its ability to carry other strategic stores. The developmental program of the GAM-77 Hound Dog missile will be completed by mid-1961. The air-to-surface missile has a maximum range of 634 nautical miles and can deliver a nuclear warhead by penetrating at high or low altitude. An advanced version of the Hound Dog, the GAM-77A, is being developed by North American. This missile will have an increased range capability of up to 700 nautical miles and will be equipped with a cartridge starter, making it compatible with the quick alert concept of the B-52H. The third member of the B-52's missile arsenal is the GAM-87A Skybolt ballistic missile, currently under development by Douglas Aircraft Company. The Skybolt Provisions DEI was held at Wichita in June, when the mating of the missile to the B-52G wing was accomplished. The missile DEI was held at Culver City, California in August. The final Provisions DEI to be held at Wichita in January of 1961. GAM-87A provisions will be installed prior to the time the missile and its associated equipment become available. The maximum range capability of the ballistic missile is 1,050 nautical miles, and it can deliver a nuclear warhead on enemy targets from either high or low altitudes. When the Douglas missile reaches operational status, the Stratofortress Skybolt combination will unite the human judgment of a manned bomber with the hypersonic speed of a ballistic weapon, representing the ultimate in weapon system capability. The AN/ASG-21 fire control system is one of the major changes to the airplane configuration, which markedly improves the B-52's defense capability. The major obvious differences between the old and new systems are the tail configuration, dual search track radar, and the new 20mm Gatling gun. Well in advance of actual firing, the entire ASG-21 system underwent a thorough laboratory checkout with the aid of a complete mock-up. The dual search track radar, shown under testing conditions, operates in the KU frequency band, which minimizes interference from lower frequency X-band ECM. Static firing of the Gatling gun was accomplished near the end of the year. Close-up high-speed photography reveals the Gatling gun principle, which discharges at the rate of 4,000 rounds per minute. To date, all ground firing activities have successfully been completed. The Fire Control System Flight Test Program is currently being conducted on a prototype airplane. Approximately 60 hours of flight time with numerous fighter passes have been completed, and the results indicate that the system target detection and acquisition will meet specification requirements. Since early B-47 production, ever-increasing requirements for electrical power have presented a problem for both the Air Force and Boeing. B-52H design studies pointed out the desirability of providing electrical power supplies which would accommodate revised and improved electrical, electronic systems and components. In addition, electrical power supply and drive design changes were necessitated by cowling redevelopment of fan engines on the B-52H. The B-52H is equipped with a 120 kVA electrical power system. Power is furnished by 4 120 kVA brushless generators. The constant speed drive, which will be delivered on early B-52H airplanes, will be rated at 60 kVA, pending completion of qualification tests. Development and testing of the constant speed drive is continuing. When completed, internal changes will be made in the drive, upgrading it to 120 kVA capability. Throughout the year, several structural programs have been conducted designed to assure the structural integrity and extend the life of the B-52. One such program, the B-52G cyclic test, not yet completed, is helping to determine the fatigue-sensitive areas of the airplane structure. This is particularly significant in view of new strategic operational concepts for the B-52, such as low-level penetration. The test also provides information for establishing structural inspections and required modifications to extend the structural life of the airplane. During the past 12 months, the airplane was cyclic tested to a repeated load spectrum representative of over 200 simulated SAC missions. The test revealed some critical areas which have resulted in changes both for B-52H production and modification kits for existing B-52G models. Timely kit installation will improve the structural life of the critical areas as well as prevent premature structural failures on the SAC fleet. Results of the cyclic test have proved invaluable, both from the standpoint of locating critical fatigue areas and for calculating structural airplane life under varied planned usage. Major design changes in the airplane meant extensive flight testing for structural integrity, flight load surveys, and flutter. Among major structural integrity flight tests were those which measured airplane capabilities with and without the GAM-77 attached. Flutter tests proved, as predicted by wind tunnel findings, that the airplane was safe from flutter throughout its weight and speed range. Modification of the airplane escape system was evaluated under several flight conditions. Findings indicated that crew members have been given a greater margin of safety than ever before. This is especially true under low-level conditions. Several seat firings were conducted during the year at the Edwards Air Force Base range. An anthropometric dummy, clothed and equipped similar to a regular crew member, was ejected at altitudes of approximately 800 and 14,000 feet. During preliminary testing, changes were made to provide maximum reliability of all ejection seat components. Early in the year, an altitude record for the B-52 was set when the H prototype airplane, powered by the turbofan engines, exceeded 60,000 feet at a gross weight of 188,000 pounds. Superior performance at altitudes above 50,000 feet, the B-52 also underwent extensive testing to investigate its low-level capabilities. To meet a demonstration requirement, both a G and a D model of the missile bomber successfully flew a VFR low-level mission profile on 2 separate occasions. The course, originating from Wink, Texas, extended through 6 states, over 1,019 miles, ending in Chadron, Nebraska. The mission profiles were flown at an average altitude of 500 feet and at speeds which averaged over 400 knots for the entire flight. Further flight testing of the terrain avoidance radar was accomplished throughout the year. During this program, low-level flying has been demonstrated under instrument flight conditions, solely with reference to the terrain avoidance radar and normal flight instruments. One flight was made under these conditions for a distance of 1,000 nautical miles at an average altitude above the terrain of 750 feet and at an average airspeed of 300 knots. Tied directly to low-altitude flight tests is the operation of a Boeing-designed and built low-level flight simulator. The simulator has provided invaluable data, particularly in connection with the implementation of the terrain avoidance radar used in low-level flights. Simulated flights have enabled human factors engineers to evaluate suitability of instrumentation arrangement and determine how well the pilot performs with terrain avoidance radar while flying under simulated low-altitude conditions. Continued peak performance of the B-52 would not be possible were it not for the success of its major support groups and activities. With the addition of two on-site locations, one at Biggs Air Force Base, the other at Barksdale Air Force Base, modification and maintenance activity was expanded to 11 sky-speed bases. Provisions for both the GAM-72 and the GAM-77 were installed at depot level and sky-speed bases in a two-pronged effort to improve the missile-carrying potential of the SAC fleet as quickly as possible. The sky-speed program has continued to prove its merit as the best means of swiftly updating all models of the B-52 as each new improvement is developed. In addition to the sustained sky-speed efforts to update the fleet, Project Turnkey was initiated at Wichita to handle the largest major revision of any B-52 model. The in-plant modification program accompanies a similar effort being conducted at both Sama and Okama. 66 E-model airplanes will be modified at Wichita to increase their capacity for low-level penetration and carrying of the GAM-72 and GAM-77 missiles. As in all airplane model changes, numerous items of ground support equipment are required for maintenance and modification activity. For example, this QEC test stand was developed for testing of replacement turbofan engines. The new stand permits thorough testing and calibration of an engine, complete with accessories, before it is installed on the airplane. Previous test stands did not allow testing of engines in a complete QEC configuration. The QEC test stand would allow SAC crews to have a supply of fully tested engines on hand at all times and eliminates using airplanes for engine test beds. Should trouble develop in an engine, it could be replaced with an engine already checked out for flight. Manufacturing continued its progress in the vital area of research and development of new processes. Among the most significant was the development of the shear, or the flow turning process. It further extends manufacturing capabilities for the forming of one-piece unwelded parts, difficult shapes, such as cones, tubes, and spheres. The use of this process provides consistent production of close tolerance parts at reduced part cost. The die forming of radomes was another process developed to solve a specific manufacturing problem. The problem in this case was to find a mechanical method of producing void-free, high-temperature radomes. The absence of voids in radomes not only helps deter delamination of the layers, but also means that the part's electrical properties are improved. Die forming of this part has meant an extension of previous design limitations, enabling the production of previously difficult shapes with a significant reduction of man-hours. Before the development of the process which produced this spiral antenna, existent manufacturing techniques were unable to approach the theoretical electrical properties of such a design. Tape-controlled milling produced the part from a theoretical equation, thereby eliminating the need for dimensioning. Another support activity of the new H model included the Air Force Factory Special Training Program. Over 425 Air Force personnel this year have undergone extensive electronics and mechanical systems maintenance training at the Wichita Division. In addition to the normal in-plant training of company personnel, instructors were called upon for the first time to conduct and supervise training in the field. Training sessions to handle the rework of the B-52 fuel quantity system and installation of wing kits were conducted on-site at all sky-speed bases by Wichita instructors whose specialized knowledge made immediate training available. The history of events and activities of the B-52 in the year 1960 gives strong evidence that the manned, long-range missile bomber, more than ever before, has a vital role in the Air Force concept of military strategy. It is a proved operational weapon capable of weathering an attack and retaliating selectively and decisively against any enemy.